In 1968, NASA had a complete and tested architecture for Mars missions in the 1980s. This wasn't science fiction, it wasn't conceptual studies, it was engineered hardware with actual test data, real engines burning real propellant and producing thrust that has never been matched since. The M-1 engine generated 1.5 million pounds of thrust. That's 50% more powerful than the F-1 that sent Apollo to the moon. Aerojet built it, they test-fired it. The data exists, and it worked. The F-1A took the proven Apollo workhorse and wrung 1.8 million pounds of force from essentially the same design. Rocketdyne had validated it by 1968. Component testing was complete. Performance numbers were confirmed. It was ready for production. The Nova rocket would have used these engines to lift payloads exceeding anything we have in 2024. Direct Mars missions without orbital assembly. Single launch capability that made deep space exploration not just possible, but practical. By 1970, all of this was canceled, not because it failed, because it succeeded at the wrong political moment. The question is why? Why would NASA cancel engines that had already been successfully tested and proven? The answer involves a technology that doesn't appear in the story until later, along with a promise that turned into a 40-year disaster. There's also a mystery in the M-1 design itself, a radical combustion approach that appears nowhere in the official documentation, but shows up in classified reports from 1966. This design would resurface 50 years later at SpaceX, proving that the murdered technology was superior all along. The real cost of cancellation wasn't the $400 million spent on development. It was a number calculated in 1971 by NASA's Future Projects Division, a number that was immediately classified. We'll reveal that number and what it meant. But first, we need to understand how this capability came to exist and why anyone thought Mars was achievable in the first place. The year 1965 marked a turning point. Apollo was on track. The engineering challenges were being solved. Intensity medium. NASA's Future Projects Division received a new mandate, planned for Mars missions in the 1980s. This wasn't aspirational thinking. This was engineering backed by budget projections and congressional support. The fundamental problem was payload. Saturn V could barely send 3 men to the moon with enough equipment for a few days. Mars required 10 times that capacity. Life support for 18 months, habitats, return propulsion, and scientific equipment. The math was brutal. 2 approaches emerged, either orbital assembly of dozens of launches or a single monster rocket that could do it all in one shot. NASA chose to develop both paths at the same time. This wasn't fantasy. It was systematic engineering backed by the same budgets that were winning the moon race. The M-1 program had begun in 1962 under Aerojet, specifically to create a hydrogen upper stage engine capable of handling Mars mission durations and deep space restart requirements. Liquid oxygen and liquid hydrogen, the most efficient chemical propellant combination available. Chamber pressure of 1,000 pounds per square inch. Vacuum-specific impulse of 430 seconds. These weren't theoretical numbers. These were design specifications being validated through hardware testing. Rocketdyne, meanwhile, was pursuing the F-1A through continuous improvement of their Apollo engine. They knew they could extract more thrust from the basic design. Injector redesign reduced combustion instability by 60%. A simplified Mark 29 turbopump used fewer stages. Thrust chamber modifications allowed for higher chamber pressure, and total parts count dropped from 5,600 to 4,800 components. This wasn't reinvention. This was optimization of proven hardware. The Nova design evolved through multiple configurations. It started as Nova C8 with 8 F-1 engines in 1962. By 1968, designs included M-1 upper stages and configurations with up to 12 F-1A engines. Payload capacity to low Earth orbit ranged from 300 to 450 tons. Compare that to Saturn V's 140 tons. Compare it to anything flying today. The Mars mission profile was specific. Single launch to low Earth orbit, trans-Mars injection with M-1 upper stage, 450-day round trip with nuclear electric propulsion for return, crew of 6 to 8, total mission mass between 800 and 1,000 tons. NASA's 1968 Integrated Program Plan laid this out in detail. Launch windows, trajectory calculations, and life support requirements. This wasn't speculation. This was mission planning. Cost projections from 1968 estimated NOVA development at $4.2 billion over 8 years. First, Mars mission was projected for the 1982 to 1984 launch window. Total program cost ran between $18 and $22 billion in 1968 dollars. Expensive, certainly, but consider the context. NASA's budget in 1966 was 4.5% of federal spending. The space race was won but not yet over. Mars was the obvious next step in Cold War competition. The M-1 development timeline proceeded methodically. Contract awarded to Aerojet in 1962. Preliminary design ran from 1963 to 1964. Component testing from 1965 to 1966. Then came full engine test fires in 1967 and 1968 at the Sacramento Test Facility. The massive hydrogen flame. The test stand shaking under 1.5 million pounds of thrust. Engineers in 1960s attire watching instruments, recording data, and validating predictions. There was something unusual in those test reports, though. Combustion stability numbers that shouldn't have been possible with the documented injector design. Some engineers noticed this discrepancy. The M-1 was performing better than it should have, showing stability characteristics that exceeded theoretical predictions for its stated configuration. This anomaly wouldn't be explained for decades. Meanwhile, in 1967, a separate study group was quietly examining reusable spacecraft. Their conclusions would directly conflict with NOVA, and they had powerful political allies forming in Washington. The Marshall Space Flight Center loved NOVA. It was Wernher von Braun's vision, the logical extension of everything he'd been building since the V-2. But the new NASA administrator appointed in 1968, Thomas Paine, had different priorities. He was reading the political winds, and those winds were shifting. November 1968. Richard Nixon wins the presidency. His transition team views the space program as Kennedy's legacy, politically expendable. NASA's budget projections for the 1970s are immediately questioned. The moon race is won. Why continue spending at wartime levels? January 1969. Thomas Paine becomes NASA administrator. He faces an impossible choice: defend von Braun's Mars vision or find a politically palatable compromise. He chooses compromise. The Space Task Group is convened to chart NASA's future. The Shuttle promise emerges from this group. A reusable spacecraft presented as the cost-effective future. The September 1969 Space Task Group report claims 50 to 60 flights per year at $5 million per flight. The analysis is fundamentally flawed. The assumptions are optimistic to the point of fantasy. But it tells politicians exactly what they want to hear. Space access will become routine and cheap. NASA is presented with a false choice: the shuttle or Mars hardware. Not both. This is framed as budgetary reality, but the numbers don't support it. The real issue is political will. Nixon wants to reduce NASA's budget. The shuttle promises to do more with less. Never mind that the engineering analysis suggests otherwise. August 1969. In the triumph of Apollo 11, while the world celebrates, the M-1 program is quietly defunded. No announcement, no press conference, no justification, just a line item removed from the 1970 budget request. 7 years of development, $400 million invested, test engines producing rated thrust, canceled January 1970. The F-1A program is terminated. Rocketdyne is told to focus on Shuttle main engine development, the RS-25. A far less powerful but reusable design. The F-1A had completed 80% of its redesign work. Tooling modifications were underway. First test fire was scheduled for late 1970. Cancellation saves $45 million in immediate costs, but eliminates a proven path to heavy lift capability. June 1970. Nova is officially terminated. Von Braun is reassigned to NASA headquarters in Washington. A promotion that removes him from Marshall Space Flight Center and from engine development. The political theater is transparent. Elevate the visionary. Remove his ability to build anything. Let's examine the budget reality that supposedly justified these decisions. The M-1 program had cost $400 million over 7 years. Projected completion cost was an additional $200 million. Total, $600 million for an engine that would have enabled Mars missions. The Shuttle program would eventually cost $209 billion over its lifetime. The math wasn't about saving money, it was about political optics. The Shuttle economics were fraudulent from the start. The 1969 Space Task Group claimed 50 to 60 flights per year. Actual Shuttle performance? 4 to 5 flights per year. Claimed cost was $5 million per flight. Actual cost was $1.5 billion per flight. The projections weren't just optimistic, they were disconnected from engineering reality. But by the time this became obvious, the programs that could have given us Mars were already dead. The M-1's final test results tell the story of what was lost. The last full-duration firing in March 1968 achieved 1.52 million pounds of thrust. Vacuum-specific impulse of 432 seconds. Stable combustion across the throttle range from 65 to 100%. All performance targets met or exceeded. This wasn't a prototype struggling to meet specs. This was a mature engine ready for flight qualification. And then, in 1985, something interesting emerged. Declassified Aerojet reports revealed that late M-1 tests had used an experimental Pintle injector design. This was borrowed from TRW's work on the Lunar Module Descent Engine. A Pintle injector is radically different from traditional designs. Instead of hundreds of small injector elements, it uses a single central post for one propellant and an annular gap for the other. Elegantly simple and inherently stable. This explained the anomalous stability data from 1967. The M-1 team had secretly tested a design that was never officially documented in NASA records, and it had worked brilliantly. The Pintle injector demonstrated 99.8% combustion efficiency. It eliminated high-frequency instability issues. It reduced parts count by 85% compared to traditional injectors. And test data showed potential for throttle range from 20 to 100%. When the M-1 program was canceled, this data was filed away in Aerojet archives. Forgotten. Intensity medium. The design that could have revolutionized rocket engines was buried along with the program that discovered it. But what happened to the actual hardware? The test engines, the prototype components, and the Nova design documentation? This is where the story becomes physically painful to recount. 1971 to 1972. The physical destruction begins. M-1 test engines at Aerojet Sacramento are cut up for scrap. 2 complete engines that had fired successfully, dismantled and sold as scrap metal. Approximately 15,000 pounds of specialized tooling was disposed of. Test Stand Complex 1A was demolished in 1973. Concrete and steel that had withstood 1.5 million pounds of thrust, reduced to rubble. The brain drain compounds the physical loss. Aerojet's M-1 team is disbanded. Senior engineers retire or move to other aerospace companies. The specific expertise in large hydrogen engines scatters across the industry. Combustion stability analysis, turbo pump design, high-pressure materials science, and cryogenic propellant handling. This knowledge exists in individual minds, but the institutional capability is gone. Rocketdyne retains some F-1A design work for potential future use, but the manufacturing capability is shut down. The F-1 production line at Canoga Park closes in 1970. At peak, this facility employed 2,400 workers. By 1971, that number drops to 400. By 1972, F-1 manufacturing is completely terminated. The consequences of this become clear decades later. When NASA wants to examine F-1 engines for the Space Launch System program in 2013, they have to recover museum pieces. Engineers reverse engineer their own heritage hardware because the institutional knowledge no longer exists. The estimated cost to restart F-1 production in the 1980s? $1.2 to $1.8 billion, that's the cost of saving $45 million in 1970. In 1971, NASA's Future Projects Division undertook a study. They calculated the cost of recreating Nova-class capability after a 20-year gap. The analysis assumed development would restart in the 1990s. It accounted for recreating test facilities, rehiring and retraining a workforce, and revalidating 1960s materials and processes with 1990s safety standards. The number? $40 to $60 billion in 1971 dollars, 4 to 6 times the cost of continuous development. Adjusted for inflation to 2024 dollars, that's over $300 billion. This analysis was immediately classified. The reason is obvious. It would have been deeply embarrassing to the Shuttle decision. It would have revealed that the supposed cost savings were actually creating a strategic disaster. But the study included more than just cost projections. It included a strategic assessment. The conclusion: losing heavy lift capability would cede deep space exploration to the Soviet Union for decades. America would be confined to low Earth orbit while other nations developed cislunar infrastructure and planned Mars missions. This prediction would prove accurate, though the competitor would eventually be China rather than the Soviet Union. The documentation purge compounds the loss. Nova design documents are archived, but many detailed engineering drawings and test reports are destroyed in periodic records, purges in 1975 and 1982. NASA's institutional memory is systematically erased. The knowledge becomes irretrievable except through the scattered recollections of aging engineers. And then, in 1998, something remarkable happens. A young engineer named Tom Mueller is working on small rocket engines. He requests historical injector research from Aerojet archives. Someone finds the M-1 Pintle injector reports. Mueller studies them, the elegant simplicity, the inherent stability, and the throttling capability. Tom Mueller co-founds SpaceX. He designs the Merlin engine using Pintle injectors. The design that NASA buried in 1970 becomes the foundation for the Merlin engine that has now flown over 1,500 successful missions. The most flown liquid rocket engine configuration in history uses the technology that was classified and forgotten for 30 years. The irony is almost too perfect. By 1975, it's already clear the shuttle won't fly 50 times per year. By 1980, NASA is studying heavy lift vehicles again, essentially reinventing Nova concepts, the same payload requirements, the same mission profiles, starting from scratch because the institutional capability was deliberately destroyed. January 28, 1986, Challenger explodes 73 seconds after launch. 7 astronauts die. The shuttle's limitations are undeniable. The promise of routine, safe, and economical access to space is revealed as fantasy. The compromise that killed Nova has failed on every level. So what was actually lost? Start with the counterfactual timeline. If M-1 and Nova had continued, NASA's projections showed first Mars landing in 1982 to 1984. With continuous heavy lift capability, a Mars base by the 1990s was technically feasible. Not guaranteed, but feasible. The engineering path existed. Instead, we've sent 0 humans beyond low Earth orbit since 1972. That's 52 years confined to a region of space we reached in 1968. Not because the engineering is impossible, because the political will collapsed and the capability was destroyed. The real cost isn't measured in dollars alone. It's measured in lost exploration, lost scientific discovery, lost inspiration, an entire generation of engineers who never worked on deep space missions, an entire generation of children who grew up believing space was a place we used to go. The shuttle's legacy is written in numbers that indict every assumption that justified it. 135 flights over 30 years, average cost of $1.5 billion per flight, 2 catastrophic failures killing 14 astronauts. It never achieved any of its promised cost savings. It never achieved its promised flight rates. It never enabled the space station construction or lunar missions that were supposed to follow. The compromise that killed Nova delivered nothing it promised. The modern irony is painful to contemplate. The Space Launch System uses modified Space Shuttle main engines, the RS-25. Each one produces 512,000 pounds of thrust. That's less powerful than the F-1 from 1968, far less powerful than the F-1A that was canceled in 1970. SLS Block 1 can lift 95 tons to low Earth orbit. Nova designs from 1968 were projected at 300 to 450 tons. Starship is trying to achieve what Nova could have done 50 years ago. Not advancing beyond, recovering lost ground, and the development costs prove the 1971 analysis was conservative. SLS has cost over $27 billion from 2011 to 2024. It has flown once. The M-1 program cost $400 million over 7 years. Adjusted for inflation, that's approximately $3.5 billion in 2024 dollars. SLS costs 8 times more for less capability. We're not advancing, we're recovering. The timeline loss is staggering. 1968 to 2024 is 56 years without heavy lift capability adequate for Mars missions. NASA's current Mars mission target is the late 2030s. That will be a 70-year gap from when it was first technically feasible. 3 generations, an entire human lifetime. An estimated 90% of engineers who worked on M-1 and F-1A are deceased or retired as of 2024. The test facilities are completely lost. The manufacturing processes exist only in archived documents that may or may not be complete. Modern attempts to recreate 1960s combustion stability analysis require starting from first principles because the institutional knowledge simply doesn't exist. But the Pintle Injector story provides a strange vindication. SpaceX Merlin engines prove that the design NASA buried was not just viable, but superior. The simplicity that enables deep throttling and high reliability. The inherent stability that eliminates complex control systems. The M-1 team was right. The technology they developed was the future. It just took 50 years for anyone to notice. The decision to cancel these engines wasn't technical. It was political cowardice. Politicians chose short-term budget optics over long-term capability. Bureaucrats chose safe mediocrity over ambitious excellence. They were told the consequences. The 1971 study laid it out explicitly. They chose to classify the warning rather than heed it. And here we are, 2024, watching SpaceX and NASA try to rebuild capabilities we had in 1968, watching China announce plans for lunar bases using heavy lift vehicles, watching the strategic vulnerability that was predicted in 1971 become reality. The warning was prophetic. We ignored it anyway. Today, we face similar decisions about Artemis, about Mars missions, about sustained deep space presence, the same political pressures, the same budget arguments, the same institutional resistance to sustained ambition. History suggests we'll make the same mistakes. The pattern is clear. Ambitious programs are approved in moments of political will. They're canceled when that will fades. The capability is destroyed. Decades later, we try to recreate what we lost. The M-1 test firing footage from 1968 remains, the massive hydrogen flame, the test stand vibrating under thrust that has never been exceeded by any hydrogen engine since. Engineers watching instruments, recording success. That footage is a memorial. Not to failure, to capability that was murdered, to potential that was deliberately destroyed. The empty test stand at the former Aerojet Sacramento facility still exists, overgrown and abandoned, a monument to institutional failure, to the cost of cowardice, to 50 years of lost exploration because we chose the politically convenient lie over the difficult truth. We had the engines, we had the designs, we had the path to Mars. We chose to destroy it. That is the story. That is the cost. And that's why, in 2024, we're still trying to go where we could have gone in 1982. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.